Hello, beautiful people, and welcome to AP Chemistry Unit 1.5, Electron Configurations. In this video, we're going to take a break from the crazy math we've been doing the last few videos and simply look at the arrangement of electrons inside atoms. We'll start by taking a quick look at Coulomb's law, then we'll review how to write electron configurations using your periodic table, and then we'll look at a few short problems, and if all goes according to plan, we'll have a nice review of electron configurations. So let's get started. It's always good to start by looking at the objectives for this unit. And the learning objective for this unit is to represent the ground state electron configuration of an atom of an element or its ions using the Aufbau principle. More on that in a second. The essential knowledge. Here's our statement. The atom is composed of negatively charged electrons and a positively charged nucleus that is made of protons and neutrons. Okay, good. We'll start there. We're going to talk about Coulomb's law, which is used to calculate the force between two charged particles. And here's the formula. It'll appear on a later slide as well. In atoms and ions, the electrons can be thought of as being in shells or energy levels, and subshells, sublevels, as described by the ground state electron configuration. Inner electrons are called core electrons, and the outer electrons are called valence electrons. The electron configuration is explained by quantum mechanics as delineated in the Aufbau principle, and so on. All right, first, quick note, we do not have to know about quantum numbers. Thank you. So one less thing to worry about. Then we do have this little thing in here about ionization energy, although I think I'm going to do that in our later video when we get to section 1.7 on periodic trends, because that is one of the periodic trends, but in case you're wondering about that. Okay, so electrons are weird. Let's get into some background theory before we write some electron configurations. Electrons are weird. They're kind of like waves. No one really knows exactly where they are because they're like kind of an uncertain thing. You can't really pin down a wave. They travel like waves. Sometimes they act like particles, depending on what experiment we're using to observe them. But what we do know is that even though they're kind of moving randomly, they're kind of confined to different locations or different zones around the nucleus. And each one of those zones is called an orbital. And you may have seen pictures like this before, but this is a set of orbitals. All right, we have the s orbitals, which happen to be spherical. So if an electron's in there, it's got sort of a spherical yard it can run around in, I guess you could say. The 2s orbitals, see the s's are all spherical, and there's a 1s, a 2s, and a 3s, and they're getting progressively bigger. Followed by the 2p's, which sort of have two little parts of the backyard they can run around in. And there's one this way, one that way, and one that way, x, y, and z axes inside the atom. So that's a group of 3 p orbitals. There's also a group of 3 p orbitals on the next energy level, which is the third energy level here. So each of these rows represents an energy level. The 3ds come next in a group of 5, and they most of the time look like clover leaves, 4-leaf clovers, but this one's kind of weird looking with sort of a donut around the middle. Here's the nice thing, though. We don't really very often have to know these quantum shapes, right? They're determined mathematically. They're a wave function that shows mathematically where an electron is likely to be. What you're more likely to see is something like that, where we'll just represent them as boxes instead of these weird orbitals, okay? And so you'll see those starting with the 1s, the 2s, the 2p's, the 3s, the 3p's, and you'll see some familiarity there. But you might be wondering, what's keeping those electrons in the orbitals? Like, why don't they just fly out of the atom all the time? Well, it turns out that's due to Coulomb's law. And Coulomb's law shows the electrostatic force between two ions or two charged particles is proportional to the magnitude of their charges, Q1 and Q2, that's here, and inversely proportional to the distance between them. So this can be applied to salts, where you have a positive charge and a negative charged ions. It can also be applied within an atom to the proton and electron. The protons are positive and they're in the nucleus, they're hanging out, they're attracting the electrons because they're oppositely charged. The magnitude of that force, that attraction, is equal to the sum or the product of their charges +1 and -1 for electrons and protons, and the distance between them. So what this means is as the electrons get closer to the nucleus, the distance goes down and they're held tighter. And that's really important when we talk about these n-electron configurations and ionization energies. So a quick little intro to Coulomb's law. There is a constant in there, which you don't have to memorize, which is kind of nice. But do know the proportionalities of being proportional to the charge and inversely proportional to the distance between them. Okay, so great. We have all these orbitals where electrons can go. Where are they going to live? Where are they going to hang out? Well, they are going to follow rules. This is the predictable part of electrons. And the three rules go like this. Aufbau principle, which is a German word. Electrons will occupy orbitals of lowest energy possible. So they're going to go and get as close to the nucleus as they can, unless space runs out, which is where we get to the next part. Pauli exclusion principle. Only 2 electrons are allowed per orbital. You can have 0 in an orbital, 1 or 2, but not more than 2. And then Hund's rule, I like to call this the riding the train rule. Hund's rule is when filling orbitals of equal energy, electrons occupy 1 per orbital before doubling up. Like people going on a train. Usually people take their own seat first before sitting next to some random stranger. And then after the one person in each seat, then we usually start doubling up on that. So that's kind of how I like to think about that. Okay, so let's just start. First thing you need to know is how many electrons something has. And we just look at its atomic number. Hydrogen has atomic number of 1 electron. And we'll use these arrows to represent each electron. And that's going to go in the 1s. That's the lowest energy possible. Helium adds a second electron. There's room in that first orbital for that one, so 1s2. And we write the electron configuration with the 1s, 2s, 2p, 3 at the orbitals, and then a superscript that shows how many of each are in there. Now, lithium has filled up the first 1s and has now gone into the 2s. So it's got 1s2, 2s1. 1s2, 2s2 for beryllium, 1s2, 2s2, 2p1 for boron. We now have entered into filling up the p orbitals. The nice thing is that it's very repetitive, and you can just keep adding electrons to what's there to get the next element that you want. Now, there is a wrinkle here. Here's where boron had 1 electron in the 2p's. Carbon adds a second one into the 2p's, but because it's of equal energy and there's extra room here, it occupies 1 per orbital before doubling up. That's important. You might be asked questions about that. Nitrogen adds a third to the 2p orbitals. So we got 3 singlets, 3 partially filled orbitals, and 1 half-fill subshell of that atom. Adding 3 more electrons fills up the p's, so we go back and double them up, and now neon has all 10, and sodium adds 1 beyond that. And so we start building them up. I have 2 that I chose to just show to you real quick that are beyond those. First, I started with silicon. Okay, and silicon has 14 electrons, 3 more than sodium does. And so 2 there, 2 there, I did 1, 1, 1, and then doubled them all up. The 3s comes next because it's the next highest. You kind of have to go back and forth. If you were ever doing an orbital box diagram like this, just pick the next lowest one, wherever it is left to right. So I got up here and then I went 1 there and then the next one in the next box over because it's got to occupy its own orbital. Writing that out, I get 1s2, 2s2, 2p6, 3s2, 3p2. And then we're going to talk noble gases also, noble gas configurations on how to shorten this down into the noble gas form. Essentially, what we're going to be doing is taking the valence electrons, which are in the outermost s and p, and the core electrons and separating them. All right? And the core electrons are kind of buried underneath, and so we just represent those by using a noble gas, whatever noble gas is there at the end of the row in front of it, and then we're filling up the next orbital after that. And so there's that. Now strontium, I picked the other one, has 38 electrons. So we got to go a little bit further. And we start here with 1s, 2s, 2p, 3s, 3p's, 4s, and then I filled up all 5 of the d orbitals with 10 electrons. Then I went 4p and 5s2, which they're starting to get long here, which is why noble gas versions are kind of important and useful. You don't have to write all the time. But we condense all of the core electrons into krypton, the noble gas that has that many electrons, and then here's the valence electrons out there, the 5s2, which would be beyond that. Okay, so if you've never done electron configurations before, I do have some other videos down the playlist introducing a little bit more and some more examples. But this is my favorite part. You might be thinking, gosh, how am I going to memorize this orbital box diagram and whether the 4D comes before the 5P, and do I have to memorize these long strings of numbers? No, not if you have a periodic table. Which periodic table? It doesn't matter. Because the periodic table, and I get really excited about talking about this in class usually. What's really awesome is that the periodic table, looks the way it does for a reason. A lot of people know what the periodic table looks like, but they've never really wondered why. Like, okay, why does it look like that? Why are there 2 columns on the left, 6 on the right, this low area in the middle over here? And it's because this is set up to show you the way orbitals get filled, okay? And we've got, just go with me here, 1s is on the top row. There's only 2 boxes there because there's only 2 electrons in the 1s. Then there's the 2s and the 2p. There's 8 electrons on the second row, 8 electrons on the third row, but 10 of them are actually tucked away 1 row down for the reason. And you can see all the s's are over here, the p's are over here, the d's are over here, and the f's are down here. So the periodic table is laid out to show you the element's electron configuration. Let me show you how it works. Let's go back to one of our early ones. Okay? Hydrogen only has 1. It's in the 1s, and it's got 1s1. And lithium ends in 2s1. Okay, great. What does that mean for us? It means that hydrogen lives right there, and guess what? It's in the first row, S block, first column, if you have 1 column there and 1 column there. First row, S block, first column, 1s1. Lithium is in the second row, S block, first column, 2s1, sorry. All right, and carbon, where's carbon? Carbon is has a configuration ending in 2p2. So where does it live? In the second row, P block, second column. Okay, I just did silicon. Silicon ends in 3p2. So it lives in the third row, P block, second column. I could do this all day. Finally, strontium ends in 5s2. So it's in the fifth row, S block, second column. That's where it lives on the periodic table. So the periodic table looks the way it does because of electrons. And what's great is you can use the periodic table to write the configuration for any element that you want. Here's a slightly different version. Okay. And for example, if I wanted to do chlorine, for example, chlorine, I go find it on the periodic table, lives right here, 3p5. It's in the third row, P block, fifth column. This is the D block, F block. And so if I was building its configuration, I simply start at the upper left, read it like a paragraph, and just make it there. So I go through the 1s, 2, 2s, both of them, so 2s2, 2p, 6, 3s2, and now I'm in the 3p's, and I'm only going to go 5 out of 6, so I'm going to end at 3p5, third row, P block, fifth column. Iron goes past the 4s's and starts building into the 3d's, and it's in the sixth spot over here, so 3d6 is where I would end with that one, and I just have to build up to that using all the repetition that we've used so far. Back to noble gases for just a moment. I have 2 configurations here. Quick, pause the video a moment, see if you can identify these 2 elements by their configurations. I'll see you back here in a second. All right, and if you identified them as sodium and sulfur, then congratulations, you got a couple of electron configurations correct. Now we use the noble gas configuration over here, and you can tell which noble gas to use by whichever one is in the end of the row above the element that you're doing. Both sodium and sulfur are in the third row of the periodic table. Neon is at the second row end, meaning it's representing 2 full energy levels. And then we just add the valence electrons out here to show the extras beyond that full shell. Okay, so I have to warn you off about some of the weird elements on the periodic table. You're not going to see them very often. In some cases, we're told that we're not even going to need to know them for the AP exam, but you're going to see them sometimes anyway. So here we go. All right, take a look at those transition elements. Their job in life, they decided a long, long time ago, they had a meeting and said, let's make things as complicated as we can for chemists. And they did a pretty good job of it. Take a look at the electron configurations and orbital diagrams for calcium through zinc. This is the fourth row of the periodic table all the way across. And you can see a nice pattern. 0, 1 arrow, 2 arrow, 3 arrows, 5 arrows, and what's up with that? So it turns out we have a little glitch in the system. Turns out that chromium actually took 1 out of the S and threw it over in the Ds. And it can do that because they're very similar in energy, those two levels of subshells. But by doing so, look, all of the electrons have their own little box, own little orbital. And so it spreads them out a little bit because electrons repel each other according to Coulomb's law. So they want to get space, and they're able to do that energetically. But what we end up with is a weird electron configuration. So it doesn't follow the rules. So make a little star next to that one. And we can continue on. There's the 5 again with the 2. 6, 7, 8, 10 again. Here it is. Copper does the same thing. It's like, I got 9 out of 10. I want to make it 10 out of 10. So it puts 1 over there and gives it a weird configuration, 4s1 3d10. So in summary, it's not only copper and chromium that do that. It's the things that are in their columns. The things that have D4 normally will swap 1 over and make D5. And the things that are D9 normally will swap 1 over and make D10. So take a moment and make a note of that. Sorry about those transition elements. They just do their thing. Okay, last little bit of information, some notes review. We've been doing electron configurations and writing them out. But that's just a start because elements can gain or lose electrons to become ions. Those electrons can be swapped. They can be given away, taken from somewhere else. And so the electron configuration actually changes, and we have to be able to write the new change on it. Essentially, what that means is that we have to start with the original configuration and either add electrons to it and make that number increase, or take those electrons away and clear out orbitals along the way. So, for example, cations, like metals, tend to lose electrons to become cations. And so lithium, for example, would be helium 2s1. You take away that 2s1, now it's just got 2 electrons, and so it's just like helium. We use the term isoelectronic for things that have the same configuration. So once they gain or lose electrons, they become the same isoelectronically to another atom or ion. Okay? And also, cations always get smaller than their original atoms because A, we've lost an electron, okay, we've less volume to occupy, and B, the remaining electrons are now sort of ganged up on by the protons and held a little tighter. So according to Coulomb's law, that attraction gets stronger. All right, anions do the opposite. Anions gain electrons. Those are typically the nonmetals of the periodic table. So fluorine, for example, lives in the second row, P block, fifth column, tends to gain an electron. Now it's 2s2, 2p6, which means it's isoelectronic with neon. Right? It now has 10 electrons. And what other element has 10? Neon. And so we'll see that in one of the questions. Finally, another little detail thing. Transition metal ions are weird still. They keep doing their thing. They have these configurations where the argon, or the noble gas, is followed by the s orbitals first. The s orbitals on a level get filled before the d orbitals. So 4s2, 3d6. But they also get vacated before the d orbitals in most cases. So iron by itself has 4s2, 3d6, but if it loses 2 electrons, those s orbital ones come out first. And if it loses another third electron, then it can come out of the Ds. But transition metals lose from the s orbital first. Finally, let's race through a few practice problems. Let's start with just predicting some electron configurations so that you can identify them. I've picked 6 elements. Please pause the video and see if you can come up with the correct noble gas configurations for those 5 elements. I'll see you back here in a couple seconds. Okay, and if you paused the video and wrote the configurations, these are the ones that I came up with. All right, niobium lives in the 4D row in the 3rd column, so 4D3. Krypton 5s2, 4D3. Calcium is in the 4th row, S column, 2nd block, so we need argon, 4s2. Iodine is way over there in the 5th row, P block, 5th column, so we have to build up to 5p5. Krypton 5s2, 4d10, 5p5. And then gold is the hardest one on here, and here's why. Because we have to understand that we have to take a little bit of a detour on our periodic table. So gold lives right there. And so I have to build up to originally 5d9, the 9th column over in the 5ds. So I have to go to here, which is xenon, that's the noble gas, 6s2, but here we actually take a detour down to the 4f's. Make a note on your periodic table if you have to. We take a detour here and do 4f 14 columns before we circle back and do the 5ds. We would do the same after the 7s. We go down here, 5f, and then circle back to the 6ds. So that's why I have xenon 6s1, 4f14, 5d10, and I did 6s1 because gold is in the same column as copper. D9 is going to make D10 by pulling 1 over from the S. And finally, antimony ends up at 5p3. All right, 3 quick multiple choice questions. Here we go. What is the condensed shorthand electron configuration for the phosphide ion P3-? So this is kind of a 2-step process. You have to go back and say, what's the original configuration of phosphorus going to end in? Where is it stopping at? Phosphorus is right there. 3rd row, P block, 3rd column in. So it's going to end in 3p3. But because it's 3-, we need to add 3 electrons. So instead of 3p3, we have 3p6. And the element that is in the spot occupied by 3p6 is argon. Nothing else, just argon. It is isoelectronic with, right? And here's a slightly more difficult one. We can pause the video on this, which gives a list of species with the same electron configuration, that is, species that are isoelectronic. So comparing all of those, take a moment and see if you can guess which of those is the most isoelectronic. All right, and I came down here to letter E. You had to work your way through all of them, or at least get lucky and start at E. So sulfur normally has 16 electrons. By adding 2, it's got 18. Chlorine starts with 17. By adding 1, it also makes 18. And potassium starts with 19, loses 1, and also makes 18. So all of these are actually isoelectronic with argon. And that is what you do. If you count the total electrons and they're the same, you can assume they're the isoelectronic because they'll organize themselves in the same orbitals. Finally, one last one, the overall electron configuration of the sulfide ion. Now, they don't tell us what that is. I'll give you a hint. Sulfide ion is just S2-. Is most similar to the electron configuration of, take a moment, pause the video, and see you back here in a second. So sulfur, again, starts with 16, ends up with 18, so it's like argon. So we kind of got a hint in the previous example. Potassium was also sitting there, starting with 19, ending up with 18, and so we get an isoelectronic situation. So potassium is there. Well, that was a brief history of electron configurations. I hope you found it helpful. Send me questions in the comments if you have them. In the meantime, happy studying and have a great day.